Hello everyone and welcome to today's presentation. I'm excited to have you here. Today we're going to explore the fascinating topic of retaining walls, specifically focusing on buttressed wall types. Over the next few slides, we'll cover the different types of retaining walls, their design features, and how they function to provide stability. Let's get started. Today, we're going to take a closer look at retaining walls, focusing on the different types and their construction features. Retaining walls are essential in managing soil and preventing erosion, especially on sloped terrains. There are several types of retaining walls, each suited to different situations based on factors like height, load, and aesthetic preferences. For example, gravity walls rely on their own weight to hold back soil, while cantilever walls use reinforced concrete and leverage a structural system for support. Then there are anchored walls, which are reinforced with cables or anchors embedded deep into the ground for added stability. When it comes to construction features, understanding the materials used, like concrete, stone, or brick, is crucial as it affects durability and strength. Additionally, proper drainage is a key aspect of retaining wall design to prevent water buildup that can compromise stability. Connecting all these points, choosing the right type and construction features for a retaining wall is vital for ensuring safety, longevity, and functionality in any project. A retaining wall is essentially a structure built to hold back or support soil where there's an uneven ground level. Its main purpose is to prevent the earth from sliding or collapsing, especially when there's a significant difference in elevation on either side. When we talk about the sides of the wall, one side is usually higher than the other, and that's where the soil needs to be retained. The earth materials, like soil or gravel, are kept in place by the wall, which can be on one side or both sides, depending on the situation. Now, when we build a retaining wall to raise the ground surface for a particular reason, the higher side of the wall is called the backfill. This backfill is what makes the ground higher on that side, often to create level areas or support structures. Understanding the function and design of retaining walls is crucial, especially since they play a key role in preventing erosion, supporting landscaping, or even stabilizing slopes. They're a fundamental part of many construction and engineering projects, helping us manage challenging terrains effectively. Let's talk about retaining walls and their role in supporting structures like bridges and culverts. When a wall is used to support the load of the bridge or culvert while also holding back the earth, we call it an abutment. This dual function is crucial for stability and safety. Now, if the wall is placed at some angle perpendicular to the direction of the fill, meaning it's positioned to effectively retain the approach fill of a bridge or culvert, that's called a wing wall. It acts like an extension that helps contain the earth more effectively at the ends. A retaining wall typically has three main parts: the base, the toe, and the stem. The base is the bottom part, which provides the foundation. The toe is the front part that faces outward, and the stem is the vertical or inclined section that retains the earth. An important point to remember is that the base of the wall is designed to be wider than the top. This wider base helps in distributing the pressure exerted by the retained earth more evenly and increases the stability of the entire structure. All these components work together to ensure that the structure can withstand the forces acting upon it, maintaining safety and durability. This understanding ties directly into our overall theme of structural stability and effective design. Retaining walls have a variety of important uses in construction and civil engineering. One of the primary applications is in hilly areas where they are used alongside roads to prevent soil erosion and landslides, ensuring safe and stable transportation routes. They are also commonly employed around swimming pools to hold back earth and create level surfaces for construction. You'll also see retaining walls at the ends of bridges, serving as abutments that support the bridge structure and transfer loads safely to the ground. Another significant use is in constructing buildings on sites that require filling or leveling. Here, retaining walls help create stable foundations by holding back the soil. Lastly, they are essential in the construction of underground water tanks, where they provide the necessary support and prevent soil collapse. Overall, retaining walls are versatile and crucial for stabilizing terrain and enabling various construction projects in challenging environments. Now, let's take a closer look at retaining walls, which are crucial in earth support systems. First, we have the gravity-type retaining wall. These rely on their own weight to resist the lateral pressure of the soil, making them quite stable for moderate heights. Next are semi-gravity retaining walls, which use a combination of weight and a slight reinforcement to handle larger loads. Moving on, the cantilever wall is a versatile design that comes in shapes like T, L, and reversed L. These walls use a lever arm principle, and their reinforcement provides additional strength for higher retaining needs. Then there's the counterfort retaining wall. This design incorporates vertical and horizontal supports called counterforts, which effectively transfer the load and allow for taller walls with less material. Lastly, we have the buttressed retaining wall, which features large buttresses or supports at intervals to help distribute the pressure and add stability. All these types serve different purposes based on height, load, and soil conditions. Understanding these variations helps us select the most appropriate design for each project, ensuring safety and efficiency in earth retention. So on this slide, we're talking about gravity retaining walls, which are also commonly called masonry retaining walls. These are typically built using plain concrete or stone masonry, which gives them a sturdy and durable structure. The key idea here is that these walls rely primarily on their own weight, along with the soil resting against them, to stay stable. Essentially, their stability depends on the mass of the wall itself and the pressure exerted by the soil. It's important to note that while gravity-retaining walls are effective for many applications, they might not be the most economical choice when you're dealing with high walls. As the height increases, the amount of material needed grows significantly, which can make construction more costly. Throughout this presentation, we're exploring different types of retaining walls, and understanding the mechanics behind each helps us choose the right solution for specific situations. In this case, gravity-retaining walls are a straightforward, reliable option for shorter heights, especially when cost and simplicity are priorities. Let's talk about semi-gravity walls. These walls require a larger toe, which means increasing the base width of the wall. This is crucial because it plays a major role in preventing tension from developing within the retaining wall. Essentially, by making the base wider, we enhance stability and reduce the risk of failure. Additionally, semi-gravity walls need a fairly heavy section of stem to support this wider base and handle the loads effectively. But here's a key point. Since the design relies on gravity and weight, only a small amount of steel reinforcement is needed. This helps in minimizing the size of the wall sections overall, making construction more efficient. So, in summary, semi-gravity walls balance the need for a substantial base with a relatively light reinforcement, which makes them a practical choice when you want stability without overly complex reinforcement. This ties into our overall theme of understanding different retaining wall types and their specific applications. Let's take a closer look at cantilever retaining walls. These walls are composed of two main parts: a vertical slab, which is the face of the wall, and a base slab that supports it. The base slab is divided into two regions, the front part called the toe and the rear part known as the heel. Understanding these parts helps us grasp how the wall functions to retain soil effectively. Now, to prevent the wall from sliding forward under pressure, we add a vertical projection at the base called a key. This key acts like a built-in anchor, increasing the resistance of the wall against sliding forces. Cantilever walls are quite economical, especially when the height doesn't exceed about 6 meters. Beyond that, other options might be more practical. In terms of design variations, we often see T-shaped, L-shaped, and reverse L-shaped cantilever retaining walls. These different shapes help adapt to specific site conditions and loading requirements, making the design both efficient and effective. Overall, the key takeaway is that cantilever retaining walls are a fundamental and economical solution for retaining soil, especially up to moderate heights, with various shapes to suit different needs. Now let's move on to counterfort retaining walls. These are quite similar to cantilever walls, but with a key difference. At regular intervals, they feature thin vertical concrete slabs called counterforts. These counterforts serve a crucial purpose. They tie the wall and the base slab together, essentially acting like reinforcements that improve stability. The main goal of these counterforts is to reduce shear forces and bending moments within the wall. This makes the structure much stronger and more capable of handling larger loads. You'll typically see this type of wall used when the height exceeds about 6 meters. In such cases, the added reinforcement provided by the counterforts is really beneficial, making the wall more stable and durable for taller retaining structures. So, in the overall context of retaining wall design, counterforts are an important solution when dealing with higher loads and greater heights, ensuring safety and longevity. Today, let's take a closer look at buttressed walls. These walls are quite similar in construction to counterfort retaining walls, which we've discussed earlier. The main difference is that in buttressed walls, you'll notice the presence of counterforts placed in front of the wall. These counterforts act as additional support, helping to resist the lateral pressure exerted by the backfill. However, one key aspect to keep in mind is that in buttressed walls, the projection of the heel, the part of the wall that extends beneath the backfill, is quite small. Because of this limited heel projection, the backfill contributes very little to the overall stability of the wall. This means that the wall itself needs to bear most of the load, which can be a limiting factor. As a result of this design characteristic, buttressed walls are rarely used in practice. Their limited ability to utilize backfill stability makes them less efficient compared to other types of retaining walls. Understanding these nuances helps us appreciate why certain designs are favored over others in specific situations, especially when considering stability and structural efficiency. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the different forces acting on earth-retaining structures. First, we have the weight of the wall itself, which is a fundamental force that the structure must support. This weight provides stability, but it also creates a downward force that needs to be balanced by other forces. Next, there's lateral earth pressure. This is the force exerted by the soil against the wall, and it's often the primary challenge in designing retaining structures. The pressure varies depending on soil type, moisture content, and other factors, so understanding it is crucial. We also need to consider vertical loads on the wall, which include additional weights such as surcharge loads, like vehicles or buildings, that sit on the soil's surface. These loads add to the overall force the wall must withstand. Wind pressure is another important factor, especially for taller walls or structures in windy areas. Wind can exert horizontal forces that can destabilize the wall if not properly accounted for. Speaking of horizontal forces, there are also direct horizontal loads on the wall itself, which might come from seismic activity or other dynamic forces that can influence stability. Now, water-related forces are particularly significant. Hydrostatic pressure of water acts against the wall when water is present behind or around the structure, exerting outward force that can undermine stability if not properly managed. Along with hydrostatic pressure, we have hydrostatic uplift, which is the upward force exerted by water beneath the structure, potentially causing buoyancy effects that can lift or destabilize the wall. Pore water pressure is another critical factor. It's the pressure within the soil pores caused by water infiltration. Elevated pore water pressures can reduce soil's strength and stability, leading to failure if not controlled. Finally, seepage forces arise from water movement through the soil, which can erode materials or create additional destabilizing forces on the structure. Understanding all these forces and how they interact is essential for designing safe and effective retaining structures. Each force plays a role in the overall stability, and managing them properly ensures the longevity and safety of the structure. When we talk about the stability of retaining walls, it's important to understand the various ways they can fail. One common failure mode is overturning, which happens when the wall tips over about its toe, usually due to excessive lateral pressure. Another possibility is sliding along the base, where the entire wall shifts horizontally, often caused by insufficient friction or inadequate design. We also need to consider failures related to the soil supporting the wall. If the soil loses its bearing capacity, meaning it can no longer support the load, the wall can settle or even collapse. Deep-seated shear failure is another critical concern, where failure occurs along a deep slip surface within the soil, compromising the wall's stability from within. Lastly, excessive settlement, which is uneven or significant sinking of the wall over time, can also lead to failure. These failure modes remind us how crucial it is to properly design and assess retaining walls, ensuring they can withstand various forces and soil conditions. Ultimately, understanding these potential failure mechanisms helps us create safer, more durable structures that effectively support the terrain we're working with. Now, let's take a look at the different types of failure that we might encounter. On this slide, we see two main categories: deep seeding and excessive settlement. Starting with deep seeding, this typically happens when a structure or foundation sinks more than it should into the ground. It can be caused by uneven soil properties or inadequate design considerations. Deep seeding can lead to structural issues and uneven load distribution, which can compromise the integrity of the entire system. Moving on to excessive settlement, this occurs when the ground beneath a structure compresses or shifts beyond acceptable limits. Excessive settlement can cause cracks, misalignment, or even failure of the structure over time. It's often related to soil properties, moisture content, or the load applied to the ground. Both of these failure types highlight the importance of proper site investigation and foundation design. By understanding these failure modes, we can better plan and implement measures to prevent such issues, ensuring stability and longevity of the structures we work on. Remember, identifying these problems early is key to avoiding costly repairs and safety risks down the line. Let's wrap up by talking about retaining walls. Retaining walls are essential structures used to hold back soil and prevent erosion, especially on slopes or uneven terrain. They play a crucial role in maintaining the stability of a landscape and can also add aesthetic value to a project. When designing or constructing a retaining wall, it's important to consider factors like the type of soil, the height of the wall, and the materials used to ensure durability and safety. Remember, a well-designed retaining wall not only supports the landscape, but also contributes to the overall integrity of the entire structure. So, understanding the key points about retaining walls helps us appreciate how vital they are in construction and landscape design, tying everything together in our overall theme of creating stable, functional, and beautiful environments.